All right. So now that we've talked about joint densities or joint distributions of random variables, so joint distributions tell us how two or more random variables vary together, and they allow for dependence among the random variables. Conditional distributions are tied to this because they tell us how one random variable behaves once we condition or once we take into account the value of the other random variable. Okay, so let's talk about first conditional distributions in the context of discrete random variables. So suppose we have random variables x and y. Then the conditional distribution of y given a specific realization of x specifies how y varies when x is equal to x. Okay, and this variation might change as different values of x with different values of x because of dependence. So in the discrete case, if x and y are jointly discrete with a joint mass function, write it as p sub xy, then the conditional mass function of y given x is defined as the conditional probability. So evaluated as specific value y and x. It's the conditional probability that y is equal to little y given that x is equal to x, which by just the definition of conditional probability, this is the probability that x is equal to x and y is equal to y divided by the probability that x is equal to x. This is equal to the joint mass divided by the marginal of x. This is called the conditional probability mass function of y given x. Just to be explicit, this function that we've defined here, py given x, is what's called the conditional probability mass function. Okay. So let's look at an example. Poisson binomial example. So let's let K be a Poisson random variable with mean mu. Let's let L be a Poisson random variable with mean nu. And let's suppose that K is independent of L. So both of these are discrete, they're independent, so we can write their joint mass function as the product. And we're going to define N as the sum of K plus L. So what we want to know is what is the conditional distribution of K given N. So we know that N is the sum of K and L. So if N is equal to little n, we know that k cannot be bigger than little n. So it can't be Poisson anymore because Poisson takes values on all possible integers. So what is that distribution? So in other words, k is not independent of n. Okay. Well, first thing is we know that n is Poisson with parameter mu plus nu by the superposition property of the Poisson distribution. Superposition or the reproductive property. So then given n, we know that k takes values 0, 1 up to n. And so if we take any possible value k, little k, what do we have? So what's the joint mass of k given n? By definition, it's the probability that n is equal to n and k is equal to little k. Okay. Well, no, well, it's probably that n is equal to n given k is equal to little k, which is equal to the probability that n is equal to n and k is equal to k divided by the probability that k is equal to little k. Okay, well, how do we deal with this? Well, if n is equal to little n and k is equal to k, this is L equal to n minus k, k equal to k, right? Because of the definition of n as k plus L. But now these are just products of probabilities. Oh, wait, hold on. I'm sorry. I have this backwards. This is the probability that k is equal to little k given that n is equal to little n. So we have to divide by the probability that n is equal to little n. Okay, so these, and because k and L are independent, this is probably that n is equal to, L is equal to n minus k, times probability that k is equal to little k, divided by the probability that n is equal to n. Well, now what's happening is we have an expression just in terms of mass functions of individual random variables. All of these are individually Poisson. So L is Poisson with rate nu. So this is nu to the n minus k e to the minus nu over n minus k factorial. K is with rate mu, so this is mu to the k e to the minus mu over k factorial. And n is mu plus nu, so this is mu plus nu to the n e to the minus mu quantity plus nu over n factorial. And so we can rearrange this. The factorial comes up top. We get n factorial over n minus k k. The e to the minus nu, e to the minus mu, these cancel. This, and this cancel. And so what we're left with is we have nu to the n minus k. Now let's do mu first. Mu to the k, and we can take k of the mu plus nu in the bottom and put this here. And then we have the rest is there's n minus k left over. And we have that here. And because mu and nu are both positive, these are between 0 and 1 and they add up to 1. And so this is actually the mass function, conditional on the value of n being n. This is the mass function of binomial with n trials and success probability mu over mu plus nu. Okay. So that's what a conditional distribution is. We've actually used conditional distributions earlier in the course before we formally define them, but now we finally have the means to discuss them because we've talked about joint distributions formally. So it's really just saying, okay, we have two random variables. We know how they vary together through their joint distribution, but now let's suppose we knew what one of the values was. Well, now we're going to compute, in essence, a marginal distribution of the random variable, but it's the marginal distribution concentrated to the event that the other variable takes the specific value that we've observed. And so this is actually extremely important and very valuable, and not just in probability, but in a lot of statistical applications where we observe data. So we observe some data and not others, and we want to be able to say, well, what do we think that unobserved data looks like given the information that we have? That's a conditional distribution. So we always we're constantly working with conditional distributions, conditional probabilities, and statistics. And so this is, we're getting into territory that's extremely important to master, and also can be quite difficult to understand at first because it does get a bit more subtle and a bit more technical at this stage.